Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 19, practice 1, in which we will solve our next problem, number 20, the setup of which is the following. In the problem number 20, we're given four distinct fixed coplanar circles, which for demonstration purposes I have named the circle S1, the circle S2, the circle S3, and the circle S4. And we're told that these four fixed distinct coplanar circles touch each other pairwise externally. That means that, again, for demonstration purposes, the circle S1 touches the circle S2 externally at the point A, while touching the circle S4 externally at the point D. The circle S2 touches the circle S3 externally at the point B, and the circles S3 and S4 touch each other externally at the point C. The objective of this problem is to show that either the points A, B, C, and D are concyclic, which means that in this particular case it is always possible to construct a circle, which for demonstration purposes is named S, and that is shown in red, that contains all four tangency points A, B, C, D, or where to show that the quadrilateral A, B, C, D is cyclic. And while it is certainly possible to generate a very straightforward proof of that statement using nothing more than the good old middle school angle chasing technology, which is based on the theorem from the theory of circles, which states that when two circles touch, whether internally or externally, the straight line that connects the centers of these tangent circles necessarily passes through the tangency points. And in this case, also, we can see that any two tangency points that belong to one circle will form a triangle that is isosceles if the vertex of that triangle is the center of the corresponding circle. By constructing the corresponding angles, it is always possible to show that, for example, the magnitude of the angle DAB added to the magnitude of the angle BCD will always amount to pi radians or 180 degrees, thus proving that the quadrilateral A, B, C, and D is cyclic. But that is not the overall objective of this problem. The overall objective of this problem is to learn how to apply the machinery of inversive geometry to the problems in mathematics that at first blush seem to not have anything in common, or that seem to have nothing to do with inversive geometry, but upon closer inspection, it turns out that inversive geometry is very much capable of solving this particular problem. As we search for an inversion of the parent plane with respect to a certain circle with a certain power and with a certain radius that will give us a competitive advantage, we make the following key observations. First, because the tangency of all the given circles in this problem is external, it follows that no 3 points of tangency are collinear. In other words, the points A, B, and C are not collinear. The points B, C, and D are not collinear. The points C, D, and A are not collinear, and the points D, A, and B are not collinear. Another observation that we make is the following. We already proved that any circle that passes through the center of inversion, whether the power of that inversion is negative or positive, will be taken into a straight line. In dealing with straight lines, in some sense, we consider to be easier or more tractable than dealing with circles. As such, in this problem, we're told that the tangency of all the circles is external and pairwise. That means that if we pick any two circles, then these two circles already pass through a common point, and such a point already plays a role of a useful candidate for the center of inversion. And for demonstration purposes, I will pick, let's say, the point A. the point A to be the center of inversion. That's number one. Number two, the power of inversion will be positive. And the third point here is needs to be discussed with the length of the radius of inversion. In this case, as I noted also in the opening lecture of this course, quite often the specific length of the radius of inversion does not matter. It is irrelevant. And in this case, in this particular problem, this is precisely the situation. The concrete or the specific length of the radius of inversion is irrelevant. And in a few seconds, I will show you an animation that makes this point quite visual. So the specific value for the radius of inversion is irrelevant, as long, of course, as that radius is a strictly positive real number. Any number that is greater than 0 is good enough. And now that we defined, for example, the point A to be the center of inversion, the inversion will be carried out with positive power with an arbitrary radius. We do not need to draw the circle of inversion. We can dispense with it already. All we have to do now is analyze where this particular inversion will take all the input objects. And that is quite straightforward. We know that the center of inversion is taken into the point at infinity, and conversely, the point at infinity will be taken into the center of inversion, the point A. The point B that captures the tangency of the circles S2 and S3 will be taken to a certain point B prime as shown over here, and B prime will be taken back into that point B. If we were to carry out the corresponding inversion right away, the point C, which captures the external tangency of the circles S3 and S4, will be taken into the point C prime, and the point C prime will be taken back into the point C. If we compose that inversion with its own copy right after it. And lastly, the point D, which captures the tangency of the circles S4 and S1, will be taken into the point D prime, as I emphasized over here. This is the point where the circles S prime 1 and S prime 4 touch. And what do the circles actually look like? Well, precisely because the circle S1 and the circle S2 pass through the center of inversion, then under the inversion defined over here at the bottom left side of your screen, these two circles will be taken into two straight lines, which are what? Which are parallel. Why is that? Well, the straight lines over here, I'll capture it this way. Straight line S prime 1 is parallel to the straight line S prime 2 for the following reason. The angle between the circles S1 and S2 is what? Well, technically, pedantically, that angle comes from the countably infinite set of real numbers, which are the integral multiples of pi, where k varies like so: 0, plus minus 1, plus minus 2, plus minus 3, and so on. But one straightforward or pleasant representative is generated when k is set to 0, 0 degrees. And in this case, if we imagine that these two circles are taken apart, then they admit the existence of two distinct internal tangents. But as two circles approach each other and then they kiss, or that they touch externally at one point, then these two distinct internal tangents degenerate into one. So these two tangents actually coincide, and the angle between two straight lines that are in some sense are parallel and also pass through one and the same point, which means precisely that the two straight lines converge into one straight line. The angle between such two straight lines is described pedantically by a countably infinite set shown over here. We take a typical representative. The angle between the tangents of these two circles is, let's say, 0, or it could be plus minus pi, again, depending on how we want to deal with this specific problem. And that means that since any inversion of the real plane with respect to a circle with either positive or negative power preserves the magnitude of the angles between the cooperating objects, it means that the angle between the images of these objects will also be the same, which is 0 degrees or plus minus pi, depending on how we want to count this. And that precisely means that the straight circle that the circle S1 will be taken into a straight line S prime 1. The circle S2 will be taken into a straight line S prime 2. And these two straight lines, S prime 1 and S prime 2, will be precisely parallel. This is also a point where we gain a competitive advantage. And the remaining observations are basically smooth sailing, because let's talk about the circle S3, for example. We know that the circle S3 touches two other circles, the circle S2 and the circle S4, and that means that precisely because the circle S3 does not pass through the center of inversion, the point A that we picked for demonstration purposes, that means that the circle S3 will be taken into a genuine circle S prime 3, but because inversion of the real plane with respect to a circle with any power preserves tangency points, that means that the image of the circle S3 or the circle S prime 3 must still touch the image of the circle S2, which is what? Which is the straight line S prime 2 shown on the right over here. And it must touch the image of the circle S4, which is what? Again, because the circle S4 does not pass through the center of inversion, the point A, it will be taken into a genuine circle. The circle S4 will be taken into a genuine circle S prime 4, but that circle, we know, touches two other circles, the circle S3 and the circle S1. And again, by the same reason, that means that the image circle S prime 4 must touch the image of the circle S1, which is what? Which is the straight line S prime 1. And we agree that the circle S prime 4 will touch the image straight line S prime 1 at the point D prime, as I showed over here. And likewise, the images of these two circles must touch each other at the image of the point C, which is the point C prime that is shown over here. And at this point, all the reflections of all the interesting objects should be clear, except for our favorite circle shown in red or in pink over here, lowercase s. Here, this is our assumption that this circle will basically pass through all four tangency points A, B, C, and D. This is what we need to prove. But if we assume that this is true, that this is the case, that there exists a circle S that contains all four tangency points A, B, C, and D, then this circle under the specified inversion will be taken into what? Well, that circle passes through the center of inversion. That means that it will be taken into what? Into a straight line. That straight line, S prime, is shown over here. This is the straight line. And we know that it is nothing to write home about if we consider the fact that 2 points, for example, B and C, we will take them as the points that we will play with. 3 circles also, nothing special. 3 distinct circles always define a unique circle. This is nothing special. We don't really need to prove anything. All the interesting battle, if you will, unfolds right around the point D. Here, we need to assume that the straight line S prime 1, which is the image of the circle S1, and the image of the circle S, or the straight line S prime, intersect. You see here they intersect over a point D prime that is initially we take to be distinct from the point D prime. So if this is, now we come down to the point where we exercise our tactical advantage in picking a successful inversion, and we see what inverted problem do we have to solve. It turns out that this is an easier to solve problem in some sense. If we can show that the straight line S prime passes through the points B, C prime, and D prime, and we show that the points D prime prime and D prime are one and the same, if we can eliminate this question mark and prove that is so, then evidently we will generate the required proof, because under the corresponding inversion, if we carry out the inversion of the parent plane with the parameters described over here for this construction, then evidently the straight line S prime, if we show that it passes through the points B prime, C prime, and D prime, and the points D prime prime and D prime coincide, it will be taken. In general, we have to be maybe somewhat pedantic and say that this straight line S prime will be taken either into itself or into a circle that passes through the point A, which is precisely what we want. But that straight line cannot be taken into itself precisely because of the observation number 1 that we made earlier. The points, no 3 points in this case, no 3 points A, B, C, and D, the tangency points are collinear. They all belong to any 3 points that we pick. They do not belong to one straight line, and that eliminates the case of the straight line S prime being taken itself to itself. Thus, by eliminate and conquer, the only choice is for the straight line S prime to be taken into a circle that passes through the point A, and that precisely means that in this case the tangency points A, B, C, and D are concyclic, belong to one circle, or that the quadrilateral ABCD is cyclic. So this is what we need to prove. And before we jump into 2 distinct proofs that I will share with you, I put together an animation for you using the free software called GeoGebra that shows that the specific radius of inversion, or the length of the radius of inversion in this case, is irrelevant. Any none greater than 0 real number will do. In the animation that you're about to see, I made the given fixed coplanar distinct circles S1, S2, S3, and S4. I showed them in dashed line. They will stay fixed, but they will be shown in dashed lines. And then the circle of inversion will be shown in black. The center of inversion will be the point A. And as the radius, or the length, the magnitude of the radius of inversion changes, you will see that the inversion circle will change its size, but overall the structure of the reflected objects that you see on the right side of your screen will remain one and the same nonetheless at all times. Once we honed in on a successful reflection or on a successful inversion of the parent plane that will give us a competitive advantage, we can proceed in multiple ways, and I will share with you 2 proofs. One proof will be based on the good old middle school angle chasing, and the other one will be based on the geometric transformation of the plane known as homothety, or uniform expansion or contraction of the plane. Here in this segment, we will discuss the proof of the problem number 20 that we're required to generate in the problem number 20 based on the middle school idea of chasing the corresponding angles. Here, this idea is based on the following. We consider 2 circles, the image circle S prime 3 and the circle image circle S prime 4. These 2 circles, we know definitely they touch at the point C prime, and in this case we have 2 and only 2 cases. The common internal tangent of these 2 circles, let's say I will mark this tangent over here. Let me carefully squeeze it in. Let's call it tau 3, 4, the common internal tangent of the image circles S prime 3 and S prime 4. So this tangent over here has 2 and only 2 possible positions with respect to the straight line, to the parallel straight lines S prime 1 and S prime 2. That tangent can so happen to be parallel to the parallel straight lines s prime 1 and s prime 2, or it can be not parallel, in which case this tangent will intersect the straight line s prime 1 at the point M and the straight line s prime 2 at the point N over here. When that common internal tangent tau 3, 4 is parallel to the image straight lines s prime 1 and s prime 2, then the proof becomes especially pleasant, because as it is evident, this straight line that connects the centers of the image circles will also coincide with our usual suspect straight line s prime. And not only that, that straight line will be perpendicular to all three lines, the common tangent and the other two parallel straight lines. And in this case, the points of tangency will coincide with their images B, C, and D. There is, in this case, there is not that much really to prove. The points D prime and D prime prime will be evidently one and the same, and the game is over. The interesting case here is when the common tangent tau 3, 4 is not parallel to the straight lines s prime 1 and s prime 2 as shown on the right side of your screen. And again, we assume that in this case that tangent intersects the straight lines s prime 1 at the point M and s prime 2 at the point N. So here we can reason as follows, and this is where the angle chasing is reflected over here in the middle of the screen. Look at the point N. The straight line s prime 2 and the common tangent in this case represent what? Two tangent segments, NB prime and NC prime. I will not be dwelling on this fact. This is already a trivial middle school unit of knowledge. The triangle NC prime B prime is isosceles because the length of the tangents drawn to a circle through a given point that is located outside that circle is one and the same. This is captured over here. The distance between the points NB prime and NC prime is one and the same. That means that the triangle, let's name the vertex N in the middle, B prime and C prime is isosceles, and that means by the famous Pons Asinorum, Euclid's Elements, Book 1, Proposition 5, the magnitude of the interior angles at the base of such a triangle is one and the same. This is captured over here. The magnitude of the angle NB prime C prime and B prime C prime is the same as the magnitude of the angle NC prime B prime. And C prime B prime shown in green, alpha and alpha, just for brevity. And what is the next maneuver? The next maneuver, we know that the angles at the vertex C prime are what? They are vertical. And that means that the magnitude of the angle NC prime B prime and C prime B prime, this angle right here, must be equal to the magnitude of the angle M C prime. And here we need to be careful which D we pick over here. Well, D prime prime, because remember, we are right now studying the interaction between which objects? The straight line s prime 1 and the straight line s prime. And that point designated with D prime prime. So the magnitude of the angle MC prime D prime prime must be the same as this. So this is alpha as well. But we see that, what do we have here? We have another theorem from Euclid's Elements, Book 1. We have a straight line S prime, this straight line shown in pink, falling on two parallel straight lines, S prime 1 and S prime 2, which are parallel. And what does it mean? By the corresponding theorem, the magnitudes of the alternate angles in this case is one and the same in plain English. This angle and this angle must be the same. And this is what is captured over here. The angle M D prime prime C must be equal to this angle right here, alpha. And that means what? Well, that means that we have, again, as I mentioned before, the angle chasing idea is that basically this angle is equal to this angle is equal to this angle is equal to this angle, alpha. That means that the magnitudes of the interior angles over here, alpha and alpha, they are one and the same, and then by the converse of pons asinorum, if the magnitude of the interior angles at the base of a triangle are equal, then such a triangle is isosceles, and that means that the length of the side MC prime is the same as the length of the side MD prime prime. Here it is important to understand that we're dealing with two primes, D prime, because so far we're studying everything as it pertains to the interaction between the straight line S prime 1 and S prime. This is the point D prime. However, now we basically turn this argument the other way around, and now we reason from the following idea. The point M is what? Is the point through which two tangents to the circle S prime 4 are constructed. The tangent MN and MD prime. In this case, the interaction is happening between we're studying the interaction between the straight line S prime 1 and the circle S prime 4, you see? And this is the interaction captured in the point D prime. In some sense here we rely on the previous proofs. We know that the image of the point D will be the point D prime, and this is precisely the point where the image of the circle S1 touches the image of the circle S4. This is the case then. So we have the distance from the point M to the point C prime equal to the distance between the points M and D prime. But here the distance between the points MC prime is one and the same. Here it's one and the same. If we equate these two guys, then we have no choice to conclude what? We have no choice to conclude that the points D prime and D prime prime, D prime and D prime prime are one and the same. So in a way we have the right to eliminate this equal sign. This is the case through the angle chasing technology, and that means that the straight line S prime passes precisely through the points B prime, C prime, and D prime, and when reflected it will be taken into a circle that passes through the center of inversion, the point A, which means that the points of external tangency of all pairwise interactions of the circles, the points A, B, C, and D are concyclic. They belong to one and the same circle S. Remember that that straight line cannot be taken into itself precisely based on our previous observation that no 3 points in this tangency point set are collinear. No such 3 points belong to one and the same straight line. Consequently, our straight line S prime will be taken into a circle that passes precisely through the point A, which concludes the proof that we're required to generate in the problem 20. And that proof is based on what? Based on the idea of chasing the angles. Now that once you understand this idea, you should probably go back on your own and generate more formal proof for the case when the common tangent to the circles S prime 3 and S prime 4, which I show over here, is intersecting the image straight lines S prime 2 and S prime 1, is parallel to this straight line. You see, it's parallel. Then what will happen to that straight line S prime? Well, it will be perpendicular, and it will necessarily pass through the centers of the circles as well, and then the proof is especially pleasant. And now for the second proof of the same statement, that is based on the idea of homothety. A proof that we are required to generate in the problem number 20 that is based on the idea of using the geometric transformation of homothety is even shorter and even sweeter than the proof that we showed a few seconds ago, and that proof unfolds as follows. It is based on the idea that the image circles S prime 3 and S prime 4 are actually the homothetical images of each other under the homothety of the parent plane that has the center precisely at the point where these two circles touch, at the point C prime. Now, homothety in plain English translates into uniform expansion or contraction of the plane, with the wrinkle that the coefficient of homothety could be positive, could be negative, and if the coefficient of homothety is negative, then after we carry out the corresponding or equivalent homothety with the positive coefficient, we basically, in plain English, flip all the vectors to their opposites. We flip all the vectors by radians, or we carry out the central symmetry for all the points of the homothetical image that was acquired when the coefficient of homothety was positive, and this is precisely the case with the tangent circles. The coefficient of homothety in this case will be negative, but that doesn't really matter. What matters here is the following. Every homothety takes any straight line into a parallel straight line. And look at how beautifully things fall into place over here. When the homothety of the parent plane is carried out with the center at the point C prime, then let's say, for example, we homothetically, in this case, it doesn't have to be that way. It could be any different correlation between the sizes, but in this case, let's say the larger image circle S prime 3 is contracted into the smaller image circle S prime 4 with the corresponding coefficient of homothety. What does that mean? It means that not only the circle S prime 3 will be taken into the circle S prime 4, but the tangent to that circle, the straight line S prime 2, will be taken into a straight line that is parallel to itself, to that line. And what is the parallel to S prime 2? The straight line S prime 1. Exactly. This is the straight line into which this tangent will be taken under the homothety when the image circle S prime 3 is homothetically taken into the circle S prime 4. And that means also that the point B prime will be taken into the point D prime. But this time we don't even need to deal with the point D prime prime. Under this homothety, the point B prime is taken into the point D prime, and conversely, if our plane is uniformly expanded and then flipped around so as to take the enlarge and then flip the circle S prime 4 into the circle S prime 3, then the straight line S prime 1 will be taken into a straight line that is parallel to it. The straight line S prime 2, again, remember this is precisely the straight lines that are parallel, and the point D prime will be taken back into the point B prime. And there you go. That precisely means that the points B prime, C prime, and D prime are collinear. It means that the straight line S prime passes precisely through these points, and again under the corresponding inversion that we already discussed in the previous segment. When we reflect this straight line in the chosen circle with the positive power once, then the choices are pedantically the following. Either the straight line S prime is taken into itself, which can never happen because no 3 points of tangency are collinear. They all belong, any 3 points do not belong to one straight line, or that straight line S prime will be taken into the circle that passes through the center of inversion, A. And that is precisely what is required to prove, and that also completes the proof. In this particular case, the tangency points A, B, C, and D belong to one and the same circle S, and we generated that proof using specifically the machinery of inversive geometry. One more time, the basic idea that leads to a successful or fruitful inversion that facilitates a straightforward proof of this in this case is the following. We pick any tangency point. It doesn't really matter. It doesn't have to be A. Any tangency point, we make the center of inversion. Any radius of inversion will do, greater than 0 with positive power once. And then the basic idea is that the center of inversion, any tangency point that we picked for the center of inversion, will flip the corresponding circles that pass through it into parallel straight lines shown here and here, the other two circles will touch each other at a particular point, and they will touch these straight lines, and then either through the idea of homothety, by observing that these 2 points are the homothetical images of each other, we can prove what we need to prove, or by using the middle school angle chasing, we can prove the same statement just as well. Now, this is it for the problem number 20. That was a very straightforward problem that I picked for a reason. We want to start the new idea, new approach with a problem that is straightforward to understand, easy to grasp, and straightforward to solve. And starting with the next problems, they will be more complicated, more difficult. And in the problem 21, we will see that inversive geometry is capable not only discovering or generating a recurrence relation. Inversive geometry can also solve that recurrence relation in a purely geometrical manner